Welcome to lesson 2.2 for Computer Science 201, Conditional Statements. A conditional statement is a statement of the form if P, then Q, or alternatively, P implies Q, and is denoted P, arrow, Q. Typically, that arrow is read as implies. P implies Q. We call P the hypothesis of the conditional and Q the conclusion. A conditional is false when P is true and Q is false. Otherwise, it is true. So the only way a conditional is deemed false, a conditional statement is deemed false, is if the hypothesis is true, but the conclusion is false. So to try to demonstrate this, I came up with a little rule I created for myself. Where if the weather is nice, then I will go for a run. So there's two statements here. The weather is nice, that's going to be our P, and then Q, and Q is I will go for a run. So this says if P, then Q. If the weather is nice, then I will go for a run. So there are only four possibilities that can happen on any given day, right? P and Q are both true. So it's true that the weather is nice, and it's true that I go for a run. Good. Followed my rule. If P is false and Q is true, so the weather is not nice, but I did go for a run, right? The weather is not nice, I still went for a run. That's okay too. I did not break the rule, right? The rule is if the weather is nice, I will go for a run. It doesn't say anything about what I will do if the weather is not nice. Okay, so that one is also followed the rule. And then for part C, P is true and Q is false. So that is the weather is nice, but I did not go for a run. Okay, then I did break my rule in that case. The weather was nice, but I did not go for a run. The rule says that if the weather is nice, I'm supposed to go for a run. And then finally, if they're both false, the weather is not nice and I did not go for a run, that does not break the rule either. That's okay. So there's only one way that this rule can be broken, or this, in other words, the statement if P then Q is considered false. And that is when P is true, but Q is false. So the hypothesis or the if part is true, but the then part is false. So we're going to use that when we do truth tables with implications. We're going to be looking for P true, Q false to give us a false implications if-then statement. Okay. In expressions that include an implication as well as other logical operators like and, or, and not, the order of operations is that the implication is performed last. All right, so let's do some practice. We're going to construct a truth table for the statement P or not Q implies not P. So there's two base statements, P and Q, so I've put them in the table first. And then following the order of operations, I need to do the not. The nots need to happen, right? So I've got the not Q and the not P. So if I'm looking at the if then, I'm going to do the implication last. So I'm going to look at the if part. Okay, so I have not Q, do the not part first, then you do the or, so P or not Q. And then since the implication comes last, I'm just going to skip over that and then do this part next. So I do the not P next. Finally, the last thing we do is the implication, P or not Q implies not P. So, with two base statements, P and Q, the options are true, true, false, false, true, false, true, false. Okay, so when P and Q are both true, let's see what happens. Let's see, not Q would be false. P or not Q. So I'm looking at a true and a false combining with an or statement. For an or statement to be true, you need at least one true for the two statements. I have one, so this becomes true. Not P, so I take the reverse truth value for P, so that's going to be false. And then finally, P or not Q implies not P. So I have this column, P or not Q is right here, and not P I have right here. And the only way that this can be false is if the if part is true, but the then part is false. So I have true, false, so this is false. Now let's fill in the rest of the columns. Okay, so not Q is going to be true, false, true. P or not Q, so I need at least one true, so true, true, true. Oops, I was looking at the wrong thing there. P or not Q. I was looking at Q. Okay, so P or not Q. So true, false, true. True, true, that should be true. False, false, that should be false, right? You need at least one true to get a true. So this is a false. And then false, true, so true. Not P is going to be just the opposite truth values from the P column. So false, true, true. And then for the implication, I'm looking to get a false. The only way to get a false is if you have a true followed by a false. So I have another one here, true, false. So that's a false. And then anything other than true, false is a true. So that's true and that's true. True, true. Number 4, here's a big one. We're going to use a truth table to show the logical equivalence of the statements P or Q implies R and P implies R and Q implies R. Okay, so remember that the implication is done last, so the P or Q has some like imaginary parentheses there. So we have 3 base statements here, P, Q, and R all show up. So I need to get all the possible true-false combinations of P, Q, and R. So I could have true, 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 false, true, false, true. So then I could have true, false, false. Those are all the ways P can be true. And then all the ways that P can be false. We could have false, true, true. We could have false, true, false. We could have false, false, true, and false, false, false. Okay, now P or Q, that's what's going to come next in this P or Q implies R statement. I am working on this one right now. P or Q implies R. The implication comes last, so the next thing I want to do is P or Q. So P or Q, you need at least, it's an or statement, you need at least one true. So I have true, 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 false, false. And then P or Q implies R. So remember, for an implication, the only way you get a false is if you have true, false. If this is true and this is false. That's the only way to get a false. So I'm going to look for true falses and put in a false. Okay, so this is true, 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 false. Okay, that one's going to be false. Then I have true, 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 false. That's another false. True, 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 false. There's another one. And then false, true, false, false. Okay, so I found 3 falses and the rest are true. Okay, P implies R. So I'm looking at this column and this column. P, if P, then R. The only way we get a false in this column is if P is true and R is false. So I'm looking for true, false. Whenever I see a true, false, I'll put in a false. So I have true, 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 false. Okay, so that second one gets a false. Then true, 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 false. Okay, fourth one gets a false. False, true, false, 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 true, false, false. So there's only two falses in this column, only two ways that P can be true and R can be false. So the rest end up true. Okay, Q implies R. Again, we're looking for true falses, right? When Q is true and R is false, you get a false here. That's the only way to get a false. So I'm looking for true, false. So I have, oops. Okay, so I have Q implies R, true, 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 false. So that gives me a false right here. Then I have false, true, false, false, true, 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 false. There's another true, false. That gets me a false right here. Then false, true, false, false. Okay, everything else is true. And then I have the final column, which is the second statement I'm looking to analyze. P implies R and Q implies R. So here's P implies R, here's Q implies R. I want to connect them with an and requires two trues. So when they're both true, I'm going to put a true here. So I have true, 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 false, false, true, 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 false, true. That's false because you need two trues to get a true. True, 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 false, false, true, 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 true. Okay, so the whole goal of this giant truth table was to compare the columns for P or Q implies R. So this one. And P implies R and Q implies R, this one. I wanted to see if they were logically equivalent by seeing if their truth tables were identical. And we have true, true, false, false, true, true, false, false, true, true, false, false, true, 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 true. So they are logically equivalent. Check. Okay, here are two more statements that are logically equivalent. Not P or Q, and P implies Q. These two are logically equivalent. I'm not going to prove it with a truth table, but we are going to just look at a quick statement that's not so mathematical and see if it makes sense to us. So saying, if you do not get to work on time, then you are fired. That's a P implies Q statement. So you do not get to work on time, that would be P. So let's call this P. You do not get to work on time. P, then you are fired. Q. So that's a P implies Q. And that's the same thing as saying get to work on time, right? So we're negating the P, not getting to work on time versus getting to work on time. So get to work on time, that would be not P, or you are fired. Q. So P implies Q is the same thing, logically equivalent to not P or Q. The negation of a conditional statement looks like this. So if you want to negate P implies Q, it's logically equivalent to P and not Q. So let's see if we can come up with a non-truth table proof. We're going to use logical equivalencies that we know and try to write a proof that doesn't involve a truth table. So not P implies Q is logically equivalent to not, okay, What we just discussed was that P implies Q is logically equivalent to not P or Q. So I'm going to replace this parenthetical P implies Q with not P or Q. We just discussed that those are the same. So I'm going to replace that with not P or Q. Then I'm going to use De Morgan's law to quote unquote distribute that negative. So I'm going to take not P, which will give me P. Then I have to flip the or over and I get an and then not Q. So the negation of P implies Q is P and not Q. Let's practice writing some negations of conditional statements. If my car is in the shop, then I cannot get to class. So this is a P implies Q, right? It's an if-then. My car is in the shop, that will be P, and I cannot get to class, that will be Q. So if I want to take the negation of P implies Q, we just discussed in the previous example that that is logically equivalent to P and not Q. All right, so P is my car is in the shop. And not Q. So Q is I cannot get to class, which means Q is I can get to class. So hopefully that feels like the negation, right? If my car is in the shop, then I cannot get to class. The opposite of that is that my car is in the shop and I can get to class. All right, another one would be if Sarah lives in Athens, so that'll be my P, Sarah lives in Athens, then she lives in Greece, Q. So the negation of P implies Q, again, is P and not Q. So P is Sarah lives in Athens. Sarah lives in Athens. And not Q, she doesn't live in Greece. Okay, so she must live in Athens, Georgia or something. The contrapositive of a conditional statement of the form if P then Q is if not Q, then not P. So symbolically, the contrapositive of P implies Q is not Q implies not P. A conditional statement is logically equivalent to its contrapositive. Okay, this is a widely used logical equivalence, very common. A conditional statement is logically equivalent to its contrapositive. So let's write each of these in its equivalent contrapositive form, and hopefully we'll be able to see that they are equivalent intuitively. So A says that if Howard can swim across the lake, then Howard can swim to the island. I think it's helpful if I draw a little picture of what we're discussing here. We've got a lake. Let's say it's roughly round. We'll put an island somewhere in it. Island. Then we're saying if Howard can swim directly across the center of the lake, if he can make that swim, then he should be able to swim to the island from anywhere in the lake. If he can go all the way across, then he can get to the island because all the way across is a longer distance than to the island. So to take the contrapositive would be to say not Q implies not P. So if not Q, right? So Howard can swim to the island, that's Q. Howard can swim across the lake, that's P. So not Q. If Howard cannot swim to the island, right? If he's not strong enough to swim to the island, then he's definitely not strong enough to swim across the lake, because it's further. Okay, another example would be, if today is Easter, then tomorrow is Monday. That's a true statement because Easter is always on a Sunday. So we'll call today is Easter P and tomorrow is Monday Q. So not Q implies not P would say that if tomorrow is not Monday, that's not Q, then not P would be today is not Easter, which is true. Okay, those are equivalent statements. The converse of a conditional statement, different from the contrapositive, the converse of if P then Q is if Q then P. So symbolically, P implies Q, its converse is Q implies P. And the inverse of if P then Q is if not P, then not Q. Symbolically, P implies Q, the inverse is not P implies not Q. Just found a typo. That should be the inverse. Okay, let's write the converse and the inverse of each of the following statements. Okay, so the same two statements that we did the contrapositive of, and we were able to see that the contrapositive does have the same meaning as the original statement. We're going to look at the converse and the inverse and see that they do not. Okay, so converse of if Howard can swim across the lake, then Howard can swim to the island. So the converse would be if Q then P. So it would be if Howard can swim to the island, then he can swim across the lake. Right, which is not necessarily true, right? Remember the picture of the lake? There's an island in it. So just because he can swim to the island does not mean that he can swim all the way across the lake. So not necessarily true. And then the inverse is not P implies not Q. So there's my P. There's my Q. Not P implies not Q is the inverse. So if H cannot swim across the lake, then he cannot swim to the island. Right? And that is also not necessarily true. Just because he can't get all the way across doesn't mean he can't get to the island, because the island is shorter. So you can see the converse and the inverse do not seem to be logically equivalent to the original statement in the way that the contrapositive is. All right, I'm going to skip the Easter and Monday example. Go to number 14. So based on those examples, it should be clear that a conditional statement is not logically equivalent to either its converse nor its inverse. A biconditional statement is of the form P if and only if Q. We denote it P with a double arrow Q. It means P implies Q and Q implies P. So this arrow goes both ways. P implies Q and Q implies P. And the words if and only if in the definition of a biconditional are sometimes abbreviated IFF. To create a truth table for the biconditional P if and only if Q, we have two base statements, P and Q, so I will fill in their potential truth values. Okay, and then the definition of P if and only if Q is P implies Q and Q implies P. So I have to break that down into the P implies Q and Q implies P columns before I can make the and. Okay, so P implies Q. Remember, the only way that can be false is if you have a true P and a false Q, and that happens here. Otherwise, we have trues. And then for Q implies P, we're looking for a true Q but a false P, and a true Q, false P. That happens here. True Q, false P. That's going to be our only false. And the rest are true. And then I just have to do an and of these two columns. An and, for an and statement to be true, you need two trues. So I've got true, false, false, true. So it's interesting to note here, a biconditional statement is true if both P and Q have the same truth value. Okay, so let's just highlight the times when it was true. P and Q were both true, or P and Q were both false. And when we got a false for the biconditional, P and Q had opposite truth values. Okay, so a summary for all the order of operations for logical operators that we have thus far. You do negations first. Obviously, parentheses is the very first thing. But then you do negations. Then you do ands and ors. And if you have both ands and ors, parentheses may be needed to be explicit about what the order is. And then you do implications third and biconditional statements third. When both are present, you'll need parentheses. All right, rewrite the following statement as a conjunction of two if-then statements. The computer program is correct if and only if it produces correct answers for all possible sets of input data. So the computer program is correct, we'll call that P. And it produces correct answers. I'm not going to write the whole thing, rest of that, but we'll call that Q. Okay, so if and only if means biconditional. So this is P double arrow Q, which is logically equivalent to P implies Q and Q implies P. So P implies Q says that if the computer program is correct, then it produces correct answers for all possible sets of input data. And then the Q implies P says that if it produces correct answers for all possible sets of input data, then the computer program is correct. Okay, so those are the two implications, and we have to connect them with an and. Okay, so there's a little bit of vocabulary here. If R and S are statements, then we say R is a sufficient condition for S, means that if R, then S. So if R happens, then S happens. So that is a sufficient, R is a sufficient condition for S. If you know R, you know S happens, okay? And then we can also have a different kind of condition, which is a necessary condition, which says that if not R, then not S. So R needs to be in place in order to get S, but it's not the only thing that needs to be in place. For example, is birth in the United States a necessary or sufficient condition for U.S. citizenship? Is it necessary? Okay, so is it necessary that you are born in the United States to be a citizen? No, it's not necessary because there are other ways to become a citizen, but it is sufficient. It is a way, okay? So it is a sufficient condition, which means if you were born in the United States, then you are a U.S. citizen. So it is sufficient. Now, the other terminology, necessary, is attaining the age of 35 a necessary or sufficient condition for being president of the United States? It is necessary. You must be 35 to be president of the United States. If you're not 35, then you cannot be president, right? So it is necessary, but it's definitely not sufficient. Being 35 is not enough to get you to be president. Otherwise, we'd have a lot of presidents, right? So it's not the fact that if you're 35, then you're president, but it is a necessary condition.